मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी राजधानी।
Well, dear students, this is 22nd lecture in the series of mechanics of metal forming. If you recall back, we started the continuation of slip line theory, and from the last lecture, if we recall, there are four types of surfaces that could be we come across while constructing slip lines. So, one which was the free surface, and on the free surface when slip line are to be drawn, that we could see that it is always meeting at 45 degree, and on the free surface there is no any interface. Therefore, the three different other surfaces are the interface, the interfaced surfaces. The first one where there is an interface with zero friction, that is frictionless interface. Secondly, when the interface with rolling friction, and third one could be interface with sticking friction. So, we would be looking into in this lecture these three different types of interfaces. So, if you recall back the figure 13 where the free surface, so for frictionless interface at any smooth or frictionless interface, there is no shear component therefore of the stress which is parallel to the interface. The slip lines therefore must be interface at plus minus 45 degree. That you can see even the previous figure number 13. Since the principal stress normal to the interface, that is sigma 1, is rarely 0, and therefore prior knowledge of the principal stresses is very much required before alpha and beta lines can be identified. Now look at this figure 14, the 14 where this is what is being shown, the frictionless interface where there is a friction, and therefore the stress, that is the shear stress sigma xy, is equal to nu q, where q is the pressure on the, because the interface two bodies are in contact. So, if this interface is taken as the frictionless, so this shear stress would be equal to nu q, where the q is your load acting on the surface, and this is what is being O, point O, and the interface which becomes a sliding friction. So, that is the sliding friction, and so the alpha and beta lines are constructed. One can see the angle psi here, and these alpha and beta lines at the point of contact at the interface point O is at 90 degree as here. So, if you look at the stresses at point O, which is shown here at the right side of the figure number 14, that has sliding friction. So, when there is a friction, sliding friction, one can now see that nu q, k is the shear stress again, and psi is the angle between these two, and here is again. So, this triangle is of very importance, where the three forces are forming a balance, and therefore, this triangle can be formed. When we see the interface with sliding friction, and if the interface has a coefficient of friction nu, that is a constant at every point on the interface, the shear stress component, that is sigma xy, which is parallel to the interface, will be simply nu q. For a normal stress q, therefore, as shown here, if the slip lines now meet the surface at any angle, say psi and say 90 plus psi, corresponding to the alpha and beta respectively, the value of psi can be evaluated from the Mohr circle. Therefore, if you recall back the Mohr circle construction, which was shown in figure number 2. So, in the Mohr circle, the shear stress, that is the sigma xy, which is acting on a plane inclined at an angle psi to the plane of maximum shear stress k, that is the slip line, can be taken directly from the Mohr circle. Look at the figure 2. So, at 2 psi angle from the direction of the maximum shear stress, that one can write that sigma xy is equal to nu q, and that is what is equal to k cos 2 psi, and r, the psi can be evaluated as half of cos inverse nu q by k, and this is what is being shown here in equation 35 and 36 respectively. This equation, however, requires prior knowledge of the principal stress, that is q at the interface, which in fact cannot be determined until the slip line field is constructed. So, the approach usually followed is therefore an iterative one, where the slip line field is first drawn, assuming that the interface to be frictionless, that is psi is equal to plus minus 45, and the normal stress is evaluated as some value of say q star, and when we assume that q is equal to q star, the value of psi can be evaluated from the equation which is shown here in 36. So, for most of the purposes, one iteration or two iteration may yield sufficiently very accurate result, but for better accuracy we should go further iterations, and so that a reasonable accuracy result is obtained. So, this is what we can construct for the sliding friction. So, you have to start with first with frictionless boundary interface, and then you go ahead with the iteration process. Secondly, let us see the second interface, which is sticking friction. So, under sticking friction condition, there is no interfacial movement, and the material at the interface will lead or will yield with the shear stress, which is tangential to the interface, reaches the yield point, yield stress in fact, which is the value of yield stress is equal to k of the material say. Thus, under sticking friction condition at the interface, when sigma xy becomes equal to shear stress k, we can replace the value q nu q by k, that is in the previous equation number 36, and that will give cos 2 psi is equal to 1, or psi is simply equal to 0 for sticking condition. So, under such condition the interface is often referred to as being perfectly rough, since the maximum permissible value of the frictional stress cannot be greater than K. The slip lines therefore meet the perfectly rough interface at 0 and 90 degree, which is shown here in figure number 15. So, you see here in equation 15, this is what is the shear stress sigma xy is equal to K, and this is what is the slip line alpha line and the corresponding beta line. So, this is the interface with sticking friction and Q is here. So, this way we can construct any slip line field for different situations. So, now let us look into how this slip line field can be plotted for a general way, so that a complete solution for a plastic deformation problem could be obtained. So, let us see the construction of slip line fields. As you know, a complete solution for a plastic deformation problem, when you are and with the application of slip line field theory, you require two things. Number one, a statistically admissible stress field must be there, that is, it satisfies the equilibrium equation, the stress boundary condition and the yield criteria. So, three things. If a statistically admissible velocity field is taken, then it has to satisfy three things, that is, it has to satisfy the equilibrium equation, number one, secondly the stress boundary condition, and third the yield criteria has to be there. And the second point which is important, that a kinematically admissible velocity field that is compatible with the stress field and the flow of the material is also required. So, the basic approach in arriving at a solution is to first propose a solution randomly and with a starting point in the form of a slip line field, and then to show that it is a kinematically admissible, therefore, and then you can go ahead with from point to point across the net of the slip line. The field proposed therefore depends on the ingenuity of the investigator. One goes ahead. The usual approach is to start the construction of the slip line from the boundary slip lines, therefore. This is what is the usual practice. The two common methods that is very popular and it is used for developing the slip line field is known as the slip line, number one as the numerical method for constructing the slip line field, and secondly is the chord method. So, numerical method and second is the chord method. In case of numerical method, the ordinates of the point through which the slip lines are constructed are evaluated numerically. So, let us consider two known slip lines like which is shown here in figure number 16, and let us take the two known slip line out of the figure 16, and these slip lines let us be AB and AD as it is shown, and it is required to complete the net by drawing slip lines, that is BC and DC. So, if you apply onto this set of the slip line, that is AB, AD and BC, DC. So, if you apply the Henke's first theorem, what we can get? So, we can get that psi A minus psi D will be equal to psi B minus psi C, or simply we can transpose on the other side, we can simply say that psi C is equal to psi B plus psi D minus psi A. This is what is being shown here in equation number 37. Now, if you recall from the figure 16b, then we can manipulate it, and you can see here in this figure where which the first Henke's equation, and this is what is at the point C, which is and point D, that is the tangent meets at point F, and when C and F is extended, it cuts the x axis as point E, and the D, the tangent which goes, and that makes through F, point F, that makes an angle psi D here, and angle psi C is here. So, this construction, it is extended from point D here, one can see in the figure, this is what is being shown, and the details has been shown here in equation 16b. So, one can then write down that yc minus yd divided by xc minus xd is equal to tangent of half of, and the in bracket 2 terms as psi c plus psi d, and similarly corresponding to point C and B, one can write down that yc minus yb divided by xc minus xb, and that is what is equal to tangent of the, again in bracket pi by 2 plus half of the 2 term summation, that is psi c plus psi b, and that is what is equal to minus of cot 1 by 2 psi c plus psi b. This is shown here from figure 16b as equation number 38 and 39. So, if you use equation the previous equation 37 and then these subsequent two equations 38 and 39, yc and the coordinates, that is the coordinate of point C, xc and yc can be easily obtained. The procedure can be repeated many times to obtain the neighboring points as well as. So, from one point you move along these alpha beta lines, reach at the second point, and then use the Henke's first equation, and then use the equations corresponding to the point like 38 and 39, one can find out all the coordinates, and therefore all the neighboring points can be obtained. This technique of constructing the slip line field, however, is not very popular, because primarily because of it takes longer time for computation. However, if you perform it by computer, it takes faster. Therefore, the chart method is popular. So, the chart method on the other hand is a very simple graphical technique of the locating the point through which the slip lines are to be constructed. So, let us see figure number 17, where the chart method is illustrated, and consider the slip lines AB and AD here. You see here that when we are going to develop the slip line field using chart method. So, the slip lines are shown here in 17. So, there are charts are taken, say the AD, DC CB and BA, these 4 charts are of the corresponding slip line alpha and beta are taken. So, the slip line AD and AD is taken. Let us start with. So, if we move from point A to B in the slip lines and rotate through an angle psi, say delta psi alpha, a small angle, while in moving from point A to D, the rotation is therefore delta psi beta. You can look here in figure number 17, and therefore the both angles, that is delta psi alpha and delta psi beta, remain constant along the their respective slip line, which is also true with Hanke's first theorem. So, one has to note that the BE is parallel to chart AD and DE is parallel to chart AB, and therefore one can find out that these relationship, that is delta psi alpha is equal to psi C minus psi D, and that is also equal to psi B minus psi A. That is the Hanke's first equation, and similarly the delta psi beta is equal to psi A minus psi D, and that is again equal to psi B minus psi C as the Hanke's first equation. So, in order to locate point C, draw a straight line at B which is inclined at an angle delta psi beta to the straight line which is joining the line AD. The angle should be in the same sense as the angle between the normal to the slip line AB at A and B. Similarly, a straight line through D is drawn that makes an angle delta psi alpha to the straight line joining AB. So, this way one can draw it. The intersection of these lines define therefore the point C, and if you look at figure 17 here, delta psi alpha is taken in the clockwise direction from the line which is parallel to AB at point D, since the normal to the AD rotates in the clockwise direction in moving from point A to D, and similarly delta psi beta has been taken to rotate in the counterclockwise direction from the line which is parallel to AD at point B, since the normal to AB rotates this way. Okay. So, the chart BC and CD are thus known, and the slip lines are completed by making the curves which is tangential to the appropriate normals, which is shown as shown in equation figure number 17. Now, mark the tangent at B and C along beta line that intersect at delta psi B, while those at point C and D along alpha line interact at delta psi alpha angle as shown in 17, figure number 17. It is therefore often convenient to keep delta psi alpha equal to delta psi beta, or therefore one can simply say that psi beta minus psi alpha is equal to the positive value of psi D minus psi A. That is how the mod is taken. While developing the slip line field, however, this gives an equiangular mesh, which is often the case, which is one can go ahead for constructing the lines. So, the graphical method appears to be very simple. So, once we have drawn the graphically the slip line, we know the coordinates, we know the angles from one slip line, and one can go from a point either along the alpha line or along the beta line. Now, the next point is to construct hodograph. So, hodograph is nothing but using the slip lines which is finally decided, that is kinematically admissible slip line, one can now draw a velocity field. So, let us see the construction of hodograph which will give you the velocity field. So, the hodograph is nothing but the velocity diagram, and it can be drawn graphically as the slip line has been drawn, which is kinematically admissible, and that will give you a kinematically admissible velocity field which is associated with the slip line field, any of the slip line field. Therefore, the hodograph and the slip lines can be constructed at the same time. Therefore, now let us consider figure 18 here, this figure where and let us consider in this figure 18a where points A, B, C etc. on the slip lines are shown, and if say V alpha and V beta are the velocity component at A, and therefore V alpha plus dV alpha, which is the closure point, and V beta plus dV beta are the corresponding velocities at point B. Then the projection of these velocity vectors onto AB must be equal, and that is d V alpha minus V beta d psi, it must be equal to 0, and secondly dV beta minus V alpha d psi must also be equal to 0, so that the velocity equations are satisfied. Now, let us consider the hodograph or the velocity diagram where O alpha and say OA, in fact OA and OB represent the velocities of points A and B respectively. So, projections of OA and OB on AB must be equal in order to satisfy the conditions of no extension or contraction along the slip line, and therefore the vector differences, that is small ab, therefore must be perpendicular to capital AB. In general, it can be stated that therefore that the corresponding elements in the velocity field and the slip line fields are normal to each other. That is quite true. Now, consider the slip line across which there is a velocity discontinuity. If one come across the velocity discontinuity as shown here in figure number 18b, the velocity normal to this line must have the same value on both sides, while the tangential velocity will have the difference value. Let this line of velocity discontinuity be represented by slip line AB. On the hodograph, if we see, the two sides of the line are represented by AB and A dash B dash, the two parallel curves which is orthogonal to AB. Now, if you see the segments, that is AA prime or AA dash and BB dash, this represents the tangential velocity discontinuity at A and B and have the same length and are parallel to the tangents at A and B points. Thus, a slip line across which there is a velocity discontinuity will map, it maps as two parallel curves which is constructed by straight lines of equal lengths, and it is equal to the magnitude of the velocity discontinuity therefore. So, one can look here that the point A and point B, and this is what is perpendicular to AB, this one. So, AA dash or AA prime and BB dash or BB prime are parallel to tangents at A and B, which is the tangential velocity discontinuity, and therefore AA prime is equal to BB prime. So, this way one can construct the hodograph or velocity field, and one can simultaneously construct the velocity field as you go on constructing the slip line and move across the point to point, you will get the hodograph correspondingly. These two construction method, graphical construction method, slip line and from the slip line the hodograph is very important, and this construction methodology can be extended for numerous examples. So, let us now start with the application of the slip line field technique so far whatever we have learned. These techniques can be applied for many applications, and whether it is a plane strain condition with the compression, with friction, without friction, having platens, or whether it is a wire drawing problem, whether it is a the extrusion problem, whether it is a say for rolling problems. Basically, one has to remember that because the slip lines are under plane strain condition, so one can only do it for the plane strain. So, let us start with the first example where the application, and let us take with the plane strain compression with frictionless plates. So, we have two platens, upper platen and lower platen, and a piece of round ring is to be compressed. So, and let us therefore assume, because the thickness of the ring is very small, and let us take it as 2h height of the this ring, and if let us look at this figure number 19 here. So, in this figure number 19 and A part, let us see the A part, and where one can see that if the 2b is your the width, or one can have, because we take the upper and lower platen interface which is frictionless, and so if 2b is taken, so it is assumed that the b is equal to thrice h. If it is assumed, that is the width is quite enough as compared to the height, and therefore from the center line, if you assume a center line which is at the point D here, so one can see, and the upper platen, which the contact points are A, C and I, and the lower platen, the middle point, center line, say the contacts points are where this a particular slip line is now shown here. So, B and D, and it can be so. This application of slip line field for let us evaluating the pressure required for compression of the this particular rectangular block, if we are assuming. One can take even circular, but let us start with the rectangular, which is shown here in figure number 19. So, the block, this rectangular block has the thickness as 2h between the two frictionless platen, which is parallel to each other, and the width is taken as 2b, and moving with a unit speed. So when we compress, let us assume that there is a u, which is the speed of compression is say unit, and this is what is being shown here in figure 19. So, if the width w of the rectangular block is large enough as compared to the thickness, that means we would be taking as the width which is large enough, it is around 20 h. So, the metal flow during the plastic deformation would be negligible along the z direction, and thus one can say that the situation becomes equal to the strain plane strain condition, and therefore the plane strain conditions are approached in xy plane. So, for any integer value which is b by h, a network of the slip line which is consisting of a straight line as shown here in 19a can be drawn, and it can be considered for analyzing the things. Since the interface is frictionless as said earlier, the slip line must meet the die face at 45 plus minus 45 degree, as it is quite usual, the free surface, because it is a free surface. So, if we propose the velocity field, a slip line field, and therefore it indicates that the material deforms as a succession of rigid triangular blocks, which is shown in 19, and these rigid triangular blocks each is separated by a velocity discontinuity, therefore. So, where there is a crossing, that gives the velocity discontinuity. So, if we recall the material which is in region, that is here, which is region here, so it will, the whole material will slide with the same velocity. So, whether the point is at the center or any corner within this triangle. So this is what we are assuming as the block of so the block movement would be taking place. So, for the proposed field to be admissible, that is the kinematically admissible, the velocity field must be compatible with the known flow of material, and let us consider 1/4 of the system and the corresponding hodograph, which is shown here in 19b for, and one has to see that from volume constancy, that is the incompressibility condition, the velocity with which the compression material will be moving horizontally will be therefore how much? It would be equal to b by h times the normal velocity of the dies. So, the velocity field is therefore compatible with the flow of material. So, that is what is required, and in order to identify the alpha and beta lines, the known boundary conditions. What are the known boundary conditions here? That is, at point B, if we see, since the material is assumed to be rigid outside the deformation zone, that is in zone 4, if you see, the different zones are marked 1, 2, 3, 4, etc. So, if you see the zone 4 where sigma 1 is 0, and that is what is known, it is shown also. The other principal stresses, that is at B, is obviously compressive and making sigma 1 to be the algebraically greatest principal stress at B. Since sigma 1 must pass through the first and the third quadrant, so AB becomes alpha line and BC becomes therefore beta line. It is quite obvious. Since sigma 1 is 0 at B, the hydrostatic part of the pressure, that is if we say small pb at B, is obtained as K, simply the shear stress of the material K, from Mohr circuit diagram. If you look at the Mohr circuit diagram here, so moving along alpha line from B to A and using the Hanke's equation, so one can write down that P plus 2K psi is equal to C1 constant, and that gives, that is PA, which is equal to PB, and that is what is equal to K, the shear stress of the material. Since alpha line is straight, and that is psi 1 is equal to psi 2. Similarly, we can apply it for the beta line, the Hanke's equation, that is beta line BC, and the Hanke's equation would become therefore P minus 2K psi, and that is equal to constant C2, and that will give the PC is equal to PB plus and which is equal to K then, because the points PC and PB is equal to. Since beta line is also a straight line giving psi beta is equal to psi C, the hydrostatic pressure which is all along the die face is therefore equal to shear stress of the material K, and from Mohr circle from therefore gives sigma 2, the vertical principal stress, which is equal to 2K, which is compressive in nature. Thus, the mean pressure for the plane strain compression with parallel friction frictionless platen would be what? It is equal to 2K. It is clear therefore that the slip line filled solution will yield the same value for the mean pressure on the platen for all integer value of B by H. So, whether it is a 1, whether it is a 2, B by H is equal to 1, 2, 3. So, as many number you can consider, and that would be all you can calculate the mean pressure. So, this is what is the example which is illustrated. Now, let us take second example where one can consider the indentation of semi infinite mass by a flat frictionless punch. So, if we take this example, and the figure is shown here in 20th figure number 20, let us consider. So, the construction of slip line in this case can be started at the punch face. Therefore, since the punch is assumed to be frictionless, the slip lines AB and BC must meet the punch surface at what angle? At 45 degrees, and that is what is being shown here in figure 20A. Since the deformed material is constructed to move downward or laterally because of the pressure of the rigid material, it must move upward at the sides of the punch. The plastic zone therefore must extend towards the free surface along CE and AG. One can see here in figure 20A. The slip line must therefore meet the free surface at 45 degree, which is quite obvious because the free surface, and that gives the right angle triangle as CDE and AFG. One can see here, and again the compression is at the unit velocity, and therefore U is 1. So 2A is the width of the compressing tool, and the three triangles therefore are connected by fan centered slip line. This is what is called as fan centered slip line, and this is shown here. One can see the center line falls somewhere here, which passes through point F, B and D. This is what the center line passes. So using this slip line, the hodograph for this slip line can be drawn, and this is what is being shown here in figure 20b. This is valid for a frictionless punch. Please remember, the deformation pattern which is proposed is therefore admissible, it is kinematically admissible, since the velocity of the block 3 is parallel to DE, and the slip line can be identified by considering the stresses at the free surface. One can see here in the figure B, while the constructing, starting point is taken as O, point O, and it is parallel to the velocity in the region 1, and it is taken as parallel, and the unit, it is taken as unit, and from when we go from one region to another region, that is region 1 to 2, the velocity is in the direction of 1, 2, and that is how it is being drawn, 2 to 2B, 2C, and that is how the parallel charts are drawn, which is chart method is, and these are the radii it becomes. So if you see that between region 2 and 3, it is spaced at 90 degree. So the normal stress sigma 2 at E is how much? Is 0, and the other principal stress, that is sigma 1, is compressive. Therefore, if we see that DE is an what line? Alpha line, because sigma 2 is 0 in the algebraically which is the algebraically greatest principal stress. The appropriate Hanke's equation, one if you apply along line ED, so it becomes P plus 2K psi, and it is equal to C1, and if you apply it at E, the principal stress where the sigma 2 is 0, therefore PE becomes equal to shear stress of the material K, and one can calculate it from the Morse circle diagram. Since ED is a straight line, therefore PD and PE is equal to shear stress of the material K, and between D and B, the alpha line rotates clockwise through pi by 2, and therefore one can write down using the Hanke's equation, that is PB plus 2K and multiplied by minus pi by 2, and that is simply equal to PD, and that is what is equal to shear stress of the material K, or simply one can write that is PB is equal to K, and it is 1 plus pi, equal to 1 plus pi. The pressure therefore remains unchanged along BA and BC, since both are straight line. Therefore one can write that PA is equal to PB, and it is equal to PB PC, and that is what is equal to K 1 plus pi, and the major principal stresses, that is sigma 2, which is acting at the vertical direction at A and C, can now be obtained very easily using Morse circle. So, if we use the Morse circle, this particular Morse circle, so one can write down that sigma 2 at point A is equal to sigma 2 at point B, and that is what is equal to Pb plus K, and that is what is equal to K in bracket 2 plus pi. Because the stress sigma 2 is same as the indentation pressure P, which is acting along AC, therefore one can write down simply that P, that is the pressure, indentation pressure capital P by 2K becomes equal to 1 plus pi by 2, and that if you calculate the value of this, it comes out to be 2.57. So, this is what the example where we took the indentation of semi-infinite mass by a flat frictionless sponge. We would continue this lecture with more examples in the next lecture, and hopefully you are clear about the concept. So, how do we construct the slip line, and we is starting with the assumed slip line, and then we go ahead and make the three conditions of compatibility and admissibility, and then you construct a slip line, final slip line, and then with slip line the hodograph is calculated, and from the hodograph one can calculate the pressure and stresses also it can be calculated, and the Morse circle becomes easier to take help to calculate the values. So, in the next example we would be taking as other examples, and therefore you all can practice more problems when you come next time, and hopefully this will make you clear to understand the theory of slip line. I once again thank you for your patience and hearing patiently, and there would be some problems as the objective, so you can try answering on the net, and you can evaluate then your understanding. Once again I will ask you to give your feedback so that we can add some more things to this lecture. So, thank you once again, thank you.